Well, good morning, everybody, and welcome to the first of today's webinars from Smart Vision Europe. My name is Jarlath Quinn, and the first webinar that we're looking at, or the first topic that we're focusing on today, is correlation analysis. We're also doing two other webinars today, one on linear regression and the other on decision trees. These all kind of fit together in the sense that they're looking at relationships between variables. The first one I would say is a very good gateway, correlation, a very good gateway concept and tutorial to the area of linear regression. So if you're interested in both of them, you might want to log into the linear regression one that we got on later. A few housekeeping things to bear in mind is that we do record these sessions, so you'll be able to listen to them again afterwards. And there's some slideware here, so we'll email a link out to you to download the materials after the session is ended. If you think that it could have been very relevant for colleagues who are perhaps unable to attend today, it may be possible for us to arrange a private session, rerun it for you. If you can get enough of them together, the best thing to do is just send us an email or give us a call, let us know. With regard to asking questions, all the lines are muted, so we ask you to use the chat panel. And if we run out of time, we will follow up with you. We tend to follow up with people afterwards. We tend to read the questions and take stock of them and then send them answers afterwards because there's an awful lot to pack in to the hour, a lot of different techniques and a lot of different demonstrations we're going to be doing before the session ends. If you don't know who Smart Vision Europe are, we are a technology company. We're a gold accredited partner to IBM, also to Predictive Solutions, who are another analytical company, as well as Data Robot. And we specialize in advanced analytics and big data technologies, though it should be said we do commonly work with open source technologies such as R and Python and Spark, if you're aware of them. We're a relatively small organization. We're made up of a team of individuals who have very deep and extensive years of experience working in the advanced and predictive analytics software industry. We've all worked for SPSS for some point, as well as IBM. And I've personally worked for SPSS since 1995 and IBM and SAS Institute, if you've heard of them, as a analytics consultant. And that means that we've basically got a lot of experience of applying advanced analytics and data science and statistics and things like that across many different sectors over the years, including, the not-for-profit sector and the for-profit sector, retail, power utilities, water utilities, insurance companies, tech finance, that type of stuff, as well as central government, local government, and healthcare. So with that out of the way, let's talk about our first topic here, which is our first agenda, our first webinar here, which is correlations. And we're going to talk about correlations in a very structured way. We're going to start off talking about why people even use them, why they're useful. And then we're going to give you a little tutorial here on interpreting how correlations should be interpreted, especially when the SPSS system produces results, which a lot of people tend to find quite confusing to begin with. It's not that difficult to understand once you know what you're looking at, but interpreting the correlation coefficient correctly is obviously a core aspect of what we're going to be talking about today. We'll talk about bootstrapping very briefly, just show you how to do bootstrapping and what that means and why that might be useful, as well as things like using the style button within the correlations dialog to highlight strong correlations. We'll look at how correlations are calculated. We'll look at other types of correlation than the standard parametric correlation type, which is Pearson's. We're going to look at non-parametric correlations, such as Spearman's and Kendall's. And we'll end up talking about the limitations of correlations and, really how we have to interpret them with care often and the sorts of criticisms that people tend to make of them and how to counter those criticisms. Okay, why are correlations useful? Well, first of all, a correlation is a generic term that we employ in everyday speech that usually denotes something that appears to have some kind of relationship, a correlation between two factors or two elements. In analytics, in statistics, correlations are really specific values. So they refer to a particular technique that is used to calculate, to quantify a relationship between variables. So it produces a number that tells you how strong a particular type of relationship is between two factors or two fields, two variables. And this kind of analysis is very powerful because, of course, it allows us to detect whether there's a linear association to measure there, whether there's a correlation there, and also to measure the strength of it between a near infinite range of factors, such as things like what's the relationship between advertising spend and website hits. If you're promoting something, a company, you spend a lot of money on your above the line advertising. How does that affect website hits within, let's say, the next 4 weeks or so? What's the correlation? What's the correlation between product sales and competitor pricing? As competitor pricing goes up, do your product sales tend to go up, or as competitor pricing goes down, do your product sales tend to drop? You could be looking at non-human type data. So you could be looking at things like machines, which we do a lot of work in sort of what we would call predictive maintenance and proactive maintenance regimes. So you're looking at things like measurements of vibration or shock against component part failure. What's the relationship between that? Or in the environment, I've done analysis on things like the relationship between pollution in coastal areas and in maritime and serpentine, and rainfall. Rainfall tends to have an effect upon pollution measures in those areas because it leads to discharges and it leads to things like nitrates being washed down off the seas. So you can actually establish a correlation how much rainfall affects pollution. And you can look at things like education, of course, study time and examination grade, whether the degree to which the hours that a student invests in studying, the degree to which that has an effect upon their test score, if you like. And the same thing with exercise and weight loss and so forth and so forth. There's loads and loads of different relationships, such as government spending and population health outcomes. There's tons of different, as I say, a near infinite range of factors that one could establish or measure a correlation between if you have the data on it. So not only can we measure a linear relationship of correlation, we'll talk about what we mean by a linear relationship in a few moments, but not only can we measure a linear relationship of correlation, but we can also use one variable to predict the other. So for example, if we know how much we're planning to increase our spend on advertising, then we can use a correlation to accurately predict what the increase in visitors to the website is likely to be. We might be able to establish how strong the relationship is between them, and in doing so, actually use that relationship that we've established to predict and say, well, look, if we increase our advertising by 50%, how many more sales should we get, or how many more hits onto the website should we get? So that leads us to interpreting correlations. We're going to show you how to generate correlations in SPSS, but how do we make sense of them when it produces output for us? Well, first of all, a correlation value, or what's called a correlation coefficient, is a number that runs between +1 and -1. And it's not that difficult to get your head around it. If you have a correlation of +1, it usually means you've correlated the same variable against itself. So you've taken something like household income and correlated household income against household income, and that will give you a perfect one, a perfect correlation. A perfect negative correlation would be if you multiplied household income by -1 and then correlated that against the original positive value of household income, you get a perfect negative relationship. It's the opposite of it. It just means that they're both perfect relationships, but with a perfect negative relationship, it means that as one value increases, the other value decreases, and vice versa. And if you have a correlation value which is very close to 0, then it just means that there's no linear relationship there. It's just usually just a random a random cluster of points that two things don't appear to be related to one another at all. So that means that, of course, most correlations are somewhere between +1 and -1. If you got a correlation, for example, of 0.5, that would be reasonably strong correlation. You would notice that, you would see it in a chart. And in fact, we've got some charts here that can help you gain an understanding of what a strong correlation looks like compared to what a weak correlation looks like as a scatter plot. So here we have, these are called Pearson's R correlations, come from Carl Pearson. And the R refers to the number that's produced. That's the R value. So here we have an R value of 0.859. That's quite a strong correlation, isn't it? Because it's quite close, 0.859, 0.86, we're rounding up. It's quite close to a value of 1. You know, it's definitely closer to this side of the distribution than down here. And here we're looking at a chart which shows the relationship between horsepower of vehicles and the weight of that vehicle. So, you know, how heavy the car weighs. So each of these points represents a different car, a different make of car. And of course, what we're seeing is that, you know, if the car weighs a lot, then the horsepower tends to be a lot, and vice versa. If the horsepower is quite high, then the vehicle weight tends to be quite high. And that's, of course, because the thing that's driving it is usually the size of the engine, and the larger the engine, the more heavy the car is. You do see these interesting little exceptions to the rule here, these points that don't quite, you know, which are very light car here in terms of weight, but quite high horsepower, and same here. So you do get these exceptions to the rule. But that's what a strong correlation would look like here of 0.859, strong positive correlation. A weaker positive correlation is less linear in shape. You can see it doesn't regress to a straight line as much. It looks a bit more like it is roughly going up. You can imagine an average line going through this. And this is looking at time to accelerate from 0 to 60 and miles per gallon. It's basically saying if it takes a longer time to accelerate from 0 to 60, then the car tends to be more fuel efficient. But this relationship is weaker. It's, you know, it's what, half of that, nearly half of 0.859, 0.434. Here's a negative relationship. So this is quite a strong negative relationship here of minus 0.7. And this is time to accelerate from 0 to 60 by horsepower. So it's basically saying, you know, if you've got a lot of horsepower, if the car's got a lot of power, then it doesn't take as long to accelerate from 0 to 60. So you're getting a negative relationship. And at all times, it makes no difference which factor is on the x-axis and which factor is on the y-axis. Correlation's not paying attention to that whatsoever. It's just saying, you know, this is the relationship between these two variables, irrespective of how you plot them. It doesn't mean that, you know, the correlation between time to accelerate and horsepower is minus 0.7, and the correlation between horsepower and time to accelerate is also minus 0.701. So there's no direction to the relationship, if you like, just to make that clear. Okay, what about non-linear relationships? What about relationships where you get, you know, effectively a cloud of points here? Well, you can see here that the correlation value, you're rarely going to get a correlation value which is exactly 0, but it's going to get quite close to 0. So here we have the mileage of the car against miles per gallon. And of course, those two things wouldn't be related. The mileage is related more to the age of the vehicle. It's got nothing to do with the fuel efficiency. And you may even get shapes like this where you get a hook shape or a curvy linear shape. The correlation can't see curvy linear shapes. I've put a line in here to say this is the relationship the correlation can see. It can't see the curvy linear relationship here. I've created this curvy linear relationship by squaring miles per gallon and looking at against the engine size. You can see it's a negative value here for minus 0.671, even though it's a curvy linear relationship. But that's because it's effectively ignoring it and saying, well, if I just kind of pretend, or if I just act as if it's a straight relationship, then I still get, you know, reasonably strong negative correlation. It's one of the reasons, though, is a kind of a clue here that you can see that if I took the square root of miles per gallon squared and got it back into the original units, this would straighten out the relationship. And this is one of the reasons why statisticians tend to take things like logs of variables. So you might take the log of, you know, national income or the log of GDP or something like that. It's often to try and straighten out the relationship between one factor and another by transforming the values. Okay, so it's just a word of warning there that correlation can't see non-linear relationship. It is simply a measure of straight line relationships between two variables. And in Pearson's case, it's usually variables or factors which are true numbers, what we call scale or continuous or ratio or interval variables, rather than category variables like season or something like that, which might be, or month, which is a category variable. This would be much more for a number variable like income or IQ score, or, yeah, spend or, height or something like that. Okay, a word of warning. Always investigate the relationship. Always visualize the relationship. Always try to do a chart of it if you can, because you find that you can get exactly the same correlation. And this is a famous set of charts here called Anscombe's quartet. Same correlation here, even though the relationships between the two factors, X and Y here, are really different. So the first one here is kind of your traditional one. We got about, what, 10 data points here. So the correlation here is coming out as 0.82, quite a strong correlation. Here's the curvy linear relationship I was kind of talking about earlier on. You might get like growth or something like that. You might get this in economic data. Still comes out as 0.82 because the correlation is just a simplification. Or here you can get a relationship where there's clearly one big extreme, which is dragging the average up. And the correlation is a kind of average, as we'll see. It's affected by this extreme value here. And given that there's not that many points within the data set, it's more likely to be affected by a single extreme value. Still comes out as 0.82. And here we actually have two values, just two values. This is what two values look like. So you can see for the X value here, we have a value of 8. And this is probably, what, 20 or 19 or something like that. So it's just two values on X of 8 and 19. It still has to draw a line between it, still has to try to simplify that. And even that comes out as 0.82. Now, it turns out you can actually do correlations against what we call binary variables, like a one of something like a yes, no. You can do like a correlation of yes, no. If you just have two values, that's perfectly legitimate to do because it's like a plus and a minus. But nevertheless, it's kind of important to know what the relationship looks like, and therefore you should think about ways in which you can chart the relationship between the two factors just so you can make sense of the correlation, or to make sure that the correlation isn't erroneously kind of coming up with a number when in fact you should really be thinking about transforming the data or other types of correlation, which we'll see, which might help actually straighten out this relationship between one factor and another. Okay, if you want to run a correlation, then this is where you're going to do it within SPSS statistics. You're going to go to analyze, down to correlate, then to bivariate meaning pairs. And if I show you, here's an example. I'm going to do this exact example in a moment. I'm going to look at 3 variables here: current salary, beginning salary, and education level in years. So 3 number variables here. And what that's going to do is, of course, it's going to give me 3 relationships. It's going to say, here's the correlation between current salary and beginning salary. Here's the correlation between current salary and education level. And here's the correlation between beginning salary and education level. And when we run that analysis, it produces a table like this, which usually people will often find quite overwhelming because there's a lot of information in it. So let's just try and simplify it a little bit. First of all, the table's a mirror image. So these values are mirrored each way because it's showing you the correlation between current salary and beginning salary, and then the correlation between beginning salary and current salary. It's the same thing, 0.88 here. So it mirrors everything. That's the first thing. The second thing is the diagonal values are all equal to 1 because that's the variable correlated against itself, which you can imagine is just a perfect 1. So again, it's kind of redundant, not necessary. You're also seeing a significance value here. This is a significance test. That's not the correlation. Significance values show how likely one is to get a correlation like that, assuming there's no relationship between the variables. It's actually testing the null hypothesis that the correlation is 0 in the population, which we'll talk about in more detail later. But the point is, it's possible to get, as we will see, a significant correlation, even though the relationship's really, really weak. So, you might find that the correlation is actually close to 0.1, but still statistically significant. That doesn't mean it's especially interesting correlation. So, treat the significance value. Don't think that just because it's significant means it's a really interesting correlation. It doesn't mean that. And then the last thing is we get n value. That's just the number of cases that the correlation was based on. You might not have data for all of the education level records. So, you might get a different number of cases. You're looking at this is the pair, the number of cases where you have valid values for both education level and current salary, for beginning salary and education level. And it just so happens to be that in every situation here that there's 474 valid cases. Okay, so let me just run this. I'm just going to go out here and just show you how to do this. We'll go to Analyze, down to Correlate, over to Bivariate, and then I'll pick them up. There's current salary, beginning salary, and where was it? Education level in years. And if I'm just going to run with the default setting here. Just the default settings. Click OK at that point. And there you go. There's exactly the same table that we're getting coming out here that we saw earlier on, with 3 values in each cell and the relationship repeated as a mirror image each time. Well, it turns out if you go back into the dialog box, you'll notice that it's got these really useful little buttons along the bottom here. One is you can rerun the analysis, but show only the bottom half of the matrix. So show only the lower triangle, and switch off the show the correlations of each variable against itself. So you can say, look, I don't need to see that beginning salary correlated against itself is 1. I mean, of course it's 1. It's not really useful. It's just being a bit dogmatic about showing the relationships. So if I go back to, I'll go to Analyze, Correlate, Bivariate, call it up again. Notice I can switch on show only the lower triangle and switch off show diagonal. Click OK, run it again. And now, instead of having a table like this, we have a table like this. Okay, so we have current salary, because it's not repeating it, it's saying here's current salary against education level, here's beginning salary against education level, and here's beginning salary against current salary. So that's the 3 relationships that have been shown. And so a good tip is to switch these, to use these controls so that you can mask out stuff that, that isn't useful or interesting to you. If I just click back to this, something else that's you should be aware of is that you can actually double click on tables within SPSS. And if you use this little button here called the pivot controls, you can stack or layer statistics or other values on top of one another. So you can actually just zoom into it and say, look, I'm really only interested in the correlations here. And you can drill down into them. You see, I say, I want to look at the significance value, I want to look at the number of cases, or I just want to look at the correlation value here. You'll notice that these have very subtle things. They have a star, meaning the correlation is significant at the 0.01 level. That just means it's less than 1% chance that the correlation has occurred, or that the relationship is likely to occur randomly, as opposed to a single asterisk, which would be significant at the 0.05 alpha level, which is what a lot of people use as a kind of arbitrary cutoff point to say whether something is statistically significant or not. A couple of other things I just wanted to point out to you while I'm about it here is, if I just go back to this and run this again, you can actually ask it to do something called bootstrapping. So if you go to bootstrapping here, bootstrapping is where it reruns the analysis 1,000 times. So it takes 1,000 subsamples of the data over and over again. Let's just simplify it. Let's just look at current salary against beginning salary here. If I click OK on that point, you can see it's actually running correlations again and again and again. And therefore, it gives you, if you're familiar with 95% confidence intervals, this is a kind of similar sort of thing here. It's saying, look, looking at all 474 cases, we get correlation here of 0.88. When I've bootstrapped it and done many, many subsamples of the data and calculated all of the different correlations for 1,000 subsamples where I'm randomly subsampling and replacing them, the correlation could be as low as 0.843 or as high as 0.9. So it's very high. Okay, so what it's saying is it's saying if you're not sure about how reliable that correlation is, this is particularly useful, of course, if you don't have very many cases. And Bootstrap is a way for you to estimate how much the correlation is likely to vary from one sample to the next if you were to have a similar sample size and repeat it again and again. So if you've got a much smaller sample size, it makes a big difference. In fact, while we're about it, why don't I just I'm just going to do a little test here off the cuff. I'll just do random sample of 10% of the cases. Click continue here. Let's click OK. I'm not 100% sure if this will work, but we'll see. If I rerun my bivariate correlations here, let's see if it makes a difference. It may be that Yeah, so we only had 61 cases now. So we've gone to, I've randomly sampled the subsets. I've masked out. I've said, just give me a sample of 61 cases. The correlation is still 0.864. So I've got much smaller sample size here. But it means that the bootstrap now goes from 0.79. It says it could be as low as 0.79 or as high as 0.93, given the fact that we can't be as this correlation is not as reliable because we've got a much smaller sample size. So it's that kind of thing you can do to play around with the correlations. Let me just go back and make sure I'm selecting all my data again. Click all cases. I go back, clicking all cases. A couple of other things. So that's bootstrapping. Something else we can do is we can highlight the most significant correlations. So if I go back here to bivariate correlation, it's going to chuck in a whole bunch of different variables here, like months since hire and previous experience and age of employees. So now I'm going to get a really quite complicated kind of table here of output here. I've still got my bootstrapping on. That's going to take a while to do. Let me run it one more time. Make sure I remember to switch that off. Click OK. Click continue. Let's run it again. Okay, so there we go. You can see there's a lot of correlations in here. It's sometimes quite hard to see. Well, something that you should be aware of is that you've got this little style button here. And you can say, okay, look, in the style button here, I want you to look for correlations that are above, say, 0.5 or greater than or equal to 0.6 or something like that. And say, just highlight them. I'll have a color here. This color is a bit livid, so I'll just say, give me a slightly tamer color than that. So go down to, go for orange here, and we'll just go here and say, okay, let's have that a bit, and there you go, a bit paler. Click OK, click continue. Click OK again. I'll click continue and click OK again. You can see it just highlights the strongest correlations within there. You should be aware also that you can go back in the style here. You could actually say, okay, I'm interested in those. You could do like a sort of traffic light system and say, I'm going to add another layer here and say I'm interested in those. And this is often quite fussy, so don't be terribly surprised if I don't get it right first time around. But I could say I'm interested in those between 2 points. So I could say, between 0.2 and let's say, I don't know, 0.59 or something like 999 or something like that. You could do that and say, okay, I'll have that as a, as a paler color in gray or something like that. And, you could theoretically at least run those. And if it finds any, it'll highlight them for you at that point. So it's something to bear in mind. What else can we do at this stage? Oh, yes, there's one other thing I wanted to show, which I find really useful and a lot of people don't really think of, is if we look at the relationship here, again here, let's hit reset so we clear everything out. Let's just look at the relationship here between current salary and beginning salary. Just look at that on its own. Say, show me the lower triangle only, and don't show me the diagonal. So it's a really simple one. There's my correlation here, 0.880. Well, it turns out within this data set, this is a really strong correlation here between beginning salary, people's starting salary, and their salary. But I've got 3 different job categories here. So I've got, for example, clerical workers, I've got 27 custodial workers, and I've got 84 managers. And we might ask ourselves, is the correlation between beginning salary and current salary the same for each of these groups? Well, a really simple thing you can do to analyze that, if you go to data and go to split file, and I tend to go for organize output by groups because that creates separate output for me. But if you split the file by this variable job cat here, or whatever category variable you have, might be region, might be job type, it might be treatment type, it might be, a customer segment or something like that. Click continue. Okay. Nothing seems to happen, but in fact, what's happened is the split file has been switched on. And if I rerun my correlation again at this stage, I won't get 1 correlation table. I'll get 3 correlation tables, 1 for clerical, 1 for custodial, and 1 for managers. And what we see right away here is for clerical workers, the relationship between beginning salary and current salary is 0.68. And for custodial workers, it's non-existent. So there's no relationship between beginning salary and current salary for the custodial workers. It's close to 0. In fact, it's not even statistically significant. And for managers, it's up to 0.69 again. So it's kind of interesting. You've got to remember here, we've got a different number of cases, 363, 27, and 84 respectively. in each of these groups. So it's a really useful procedure to run, just to use to go to data, split file, and ask it to split up your analysis by some sort of control group or some sort of group that you're interested in, like region or something like that. It's a really good thing to do, and it'll give you separate output for that, and it allows you to try to test out lots of different hypotheses. Okay, let's explore Pearson's correlation itself. This is the one we've been using. How is it actually calculated? Well, this correlation we're looking at is called, technically it's called Pearson's correlation coefficient, or Pearson's product moment correlation. Correlations describe data moving together. That's basically the loosest description of them. But this is called a parametric procedure, and that means that it makes assumptions about the data. And strictly speaking, the correlation I've been using here, the default Pearson's R, assumes that the level of measurement of the variables is continuous or scale. So it assumes they're numbers. It does not assume they are rating scales, for example, like agreement or satisfaction. It assumes there is no extreme outliers in correlated variables. Well, they all kind of assume that, you know. You don't, any wild extremes are going to affect any analysis. It does assume that the data is normally distributed, but you know, for a reasonable sample size, and I mean by more than 30 cases or something like that, it's not really strictly enforced too much. So I don't think too many people spend too much time checking the normality, whether or not of correlation data, when you've got a reasonable sample size and it meets the other requirements or the other assumptions. The formula for Pearson's correlation looks quite scary to people. We're actually going to calculate it now. It's not that scary. It's not that difficult to get your head around. Let's see an example of it. What it's spending most of its time doing is it's looking at the difference between individual cases. This is the case on the X score. Let's call that variable one, and variable one's average for each case. So, you know, variable one has a score of 25 and the average is 30. Well, then the difference is, you know, -5, and the next case is 35 and the average is 30. Well, the next difference is, you know, is clearly +5. And it does the same for the second variable. The difference between each score and its mean, and it sums those and multiplies them together. And then it looks at the ratio of that, again, against each of the squared values of these differences, summed individually, and multiplied together, and then the square root of that. Now, I know that that's a lot to get your head around with, but actually it's, you know, you can calculate this manually. It just would take a long time. And I guess the point here is to try to emphasize that this isn't magic. You know, this is mostly looking at the ratio of differences between individual cases and their average for that overall column. So if I skip out here to SPSS again, let's just go back to and let's see an example of calculating it. How could I calculate it? Well, I've got a little syntax file here called calculate a correlation. And I'm going to open up a data set here. Really, really simple data set, which I've just called calculate a correlation. And I'm going to close the output because I don't need that now at the moment. And there's my two variables here. It's just 10 rows. Student score on a physics test, student score on a maths test. And we're told that, you know, if you're good at physics, you're good at maths and vice versa. Is this true? Is there a correlation between the two here? Well, if we went through this formula that we saw here earlier on, we could actually just calculate each of these bits in turn as separate columns and just multiply them together and get our R value here. And that's what I've done. I've said, okay, let's calculate the difference between each variable and their own mean. And it turns out the mean for physics is 3, and the mean for maths is 3.1. So I get to say, okay, let's run that, compute that, and that tells me what the difference is for each of these rows of data between their score and their mean for that subject. And then I could multiply them together. That creates a new column for me. There's the multiply them together. It's a single value. Then create two variables by squaring the two mean difference columns. Okay, that's now we're down to the second part of the equation here. So we've got two variables. This is the square of the mean differences. And you remember at the bottom here, it's looking at the square of the mean differences. So this is really talking about these points here. So we'll go back here and then the next bit says, okay, you got to work out the sum of that. It's a bit ugly, but I just did a little frequency table. It says, okay, the sum is 10 for the x mean and times the y mean. If you multiply them together, that's what that is. And it says, okay, create a variable with that value. Again, quite ugly because I have to create a variable with that value of 10. It's not like Excel where it's like a little formula I hold up here. I have to kind of, for this illustration here, create the entire column of that. And then work out the sums of squared x mean x and squared y mean y. So you work out the sums of those. There's the sums of each of them. So we've just calculated 16 and 4.9. That's what the sums of those two columns are. Compute those two. So create two columns for those two. So we're going, look, we've got two columns here at the end for those two. What we're kind of zeroing in on is our final calculation, where we say, okay, use these three columns to compute your correlation coefficient. And that's what I do. I hit run here. My correlation coefficient comes out as 0.648. Can we just check that? Let's go to bivariate correlations. Let's look at the relationship between maths and physics. Show only the lower triangle, don't show the diagonal. It's 0.648. Okay, so there is a way to do this. It's not magic. It's mostly the differences between individual cases and their means for each variable. And there's kind of a ratio between them and their squared values, but I'm not going to go into in more detail than that. So there we saw that. What about, you saw me talking about here about the fact that we've been working with scale variables thus far. What happens when we work with rank order variables? These are called ordinal fields. So these would be things like rating scales. So like, Likert scales or agreement or, level of satisfaction or something like that. Well, the thing is that these ordinal variables, which have their own special symbol in SPSS, don't have a ruler symbol, they have these little bar chart symbol here. These aren't real numbers. So, if somebody asks you, what level of satisfaction is, that's not a real number because, it's actually a numeral because it's just a rank. I mean, you could say that seasons are ordinal variable, not real numbers. You could start with spring 1, summer 2, autumn 3, and winter 4. You probably would code them in that order because the order is important, in the same sense if you were looking at, level of agreement or satisfaction or, any sort of scale where you're trying to measure something which is, about opinions. And it turns out there are two techniques in SPSS that deal with these kinds of data when it comes to correlations. One's called Spearman's, not Pearson's. It's almost an anagram of it. Spearman's rho, which rho being, once again, the Greek letter for R, so Spearman's R, and Kendall's tau B. And both of these are called non-parametric methods. That means that it doesn't make assumptions about the type of data. So Spearman's rho works by ranking the original values from the lowest to the highest. And for this reason, it's sometimes referred to as Spearman's rank correlation. And unlike Pearson's correlation here, we don't know if the two variables are linear related as ranking the values hides this relationship. You'll see an example of this. Spearman's correlation detects what are called monotonic relationships. Monotonic relationship is one which is, as the size of one variable increases, the other variable also increases, or whereas the size of one variable increases, the other variable decreases. Spearman's correlations are not affected by outliers, as we'll see why in a moment, because this takes ranks. But analysts should consider whether or not extreme outliers are valid reflections of the population under consideration. So always be a bit skeptical about outliers. So here's a non-linear relationship. This is restaurant bill against calories consumed, and it comes from this data set. And again, I've got a little data set here which I've created called the Fancy Restaurant. And let's go to output. Let's just close that down so I don't need that anymore, and I don't need the syntax anymore. Fancy Restaurant. And when I graph these two things, what's it got along the bottom there? It's got the bill along the bottom. So if I graph these two things, I'd go to Graphs, Chart Builder. I'd go down to Scatter Plot here, call up Scatter Plot, put the restaurant bill along the bottom. Not that it matters. I'm just trying to recreate the chart that you're seeing in the output here. Here it's blue rather than red. We can see the same sort of relationship here. This non-linear relationship, of course. And what's happening is that it's saying once you get above like 200 quid for your restaurant bill, I mean, you're not necessarily increasing your calories per head or per diner. It just means that you're usually expending more money. They're buying more expensive food, they're buying like the top end steaks or lobster or something like that. But it generally tends to find, if you look at the data here, that, as the restaurant bill increases, so the calories increases. If they're just having a starter or an amuse-bouche or something like that, until they're having like a, 6-course tasting menu or something like that, then the numbers tend to go up one another. Um, and if we can calculate a correlation with that, we can actually calculate a correlation with that. If I did a Pearson's correlation against those two, so just ignoring the fact that the non-linear relationship, ignoring that and click that. Pearson's correlation comes out as quite strong here at 0.864, but that's because it's effectively just putting a straight line through it. Now, weirdly, if I did a Spearman's correlation here, and I said, okay, let's do Spearman's correlation rather than Pearson, switch off Pearson so you don't get them both, so it isn't confusing. Click OK. It comes out as 1. It comes out as 1. Why is that? Well, because what Spearman's looking at is not the values, but the rank of the values. And I can show you how you get ranks of values in SPSS. If you just go to, well, where do I do this? I always forget. It's always under one of the two rank values. So rank cases, there you go there. So I'm just going to rank them. Smallest value gets a 1. Largest value gets whatever the largest number is. I don't need a summary table. Click OK. And basically, you can see why it gives you a perfect correlation, because it's saying this is the 4th most expensive. This is the 10th most expensive. This is the 10th most calorific. This is the 11th most expensive. This is the 11th most calorific. So it gives you a perfect relationship because it's looking at the rank of one against the other. And when you look at rank data, you get a perfect, relationship. You get a perfect linear relationship. It destroys the non-linear aspect of it. Look at the rank here. If I do the rank against the rank and click OK, look, you get a perfect linear relationship. So if I mess these around a bit, let's just mess them around, but let's make that one for whatever reason, £220. We'll make that one 14 quid. Make that one £155. I'll just mess this around a wee bit and make that let's say 2,699. I'll make that one 1900. I'm just messing them about. Now the ranks are not going to be perfectly in accordance with one another. I do bivariate correlation, do Spearman's again. Like, okay, it's not going to be exactly point. One of them was going to be 0.7 now because the ranks aren't exactly the same. So that just expresses or explains how Spearman's work. Now, an alternative to Spearman's, rather than just looking at the correlation between the ranks of the values, so in other words, destroying their kind of their continuous properties and simply ranking them one to the next. And Spearman's course is appropriate for rating scales because rating scales are ranks, so that's why it works against those. There is an alternative. Some people are critical of Spearman's and say it's a wee bit simplistic. There's one called Kendall's Tau B. Kendall's Tau B works by ranking the original values from the lowest to the highest. However, this time the analysis focuses on basically the degree of agreement, what it calls a concordance and discordance between the two rank columns of data. So I've got a little data set here, which is movie title. And we've got the IMDb rank from 1 to 10. And we've got the Rotten Tomatoes rank from 1 to 10 for these different movies. And you can see the level of agreement and disagreement. This one's ranked number 1, but here it's actually, this one's ranked number 1, Spencer Confidential. This one's ranked number 2, but this one's ranked number 2. So it kind of looks at the level of agreement and disagreement. And because it's doing this, it says, oh yeah, we both agree that this is the top ranked one or the bottom ranked one, which is this documentary. It kind of agrees that, these are, it looks at the relationship between each of these and each of these as a set of permutations. That means that it tends to be quite resource intensive. So if you're dealing with quite a large data set, you may find it just takes a very, very long time to calculate it, if it ever calculates it. So Kendall's Tau B tends to give smaller correlation values than Spearman's and can also take much longer to calculate. Some people say it's more accurate though and a better estimate, but the downside is that it takes longer to calculate. So let's look at the movie ratings one here. We are just talking about a moment ago. Let's go to output, make sure we destroy the output so we don't get too confused. Here's the IMDb score. Here's the Rotten Tomatoes score for these different movies. Is that what I want? Yeah, okay. Let's just do bivariate correlations. Let's look at IMDb against Rotten Tomatoes. And we'll look at Spearman's, first of all. Don't show the diagonal. Click OK. What's that get us? It gives us a correlation coefficient of 0.622. So the level of correlation between one Internet Movie Database rating and Rotten Tomatoes audience rating or critic score rating is 0.622 using Spearman's rule. Is it the same if we were using Kendall's Tau B here? Let's run that one. I'm just keeping them separate to make it obvious. It's a little bit lower here at 0.452. And what I would expect is that the highest correlation would be using Pearson's, which is 0.616. So it's actually a little bit lower, but people would argue if you're being very conservative here and you want to say, look, I want to be conservative here of estimating my correlation, that you would use Kendall's Tau B for this data here, because these are we're effectively saying these are ranks, if you like, rather than individual true scale variables. Okay. What about visualizing correlations for things like ordinal variables? You've seen me doing scatter plots here between, things like, cars and salary factors and education and stuff like that. You know how to do that. You can just go here to graphs and say, okay, I'm going to show the relationship here between, as a scatter plot here between these two variables, which is Rotten Tomatoes. I'll put up there and IMDb score down here. Click OK. So it looked like it's kind of messy. It's kind of messy, but it kind of works. They're all points. It looks a bit odd because some of these values here, they're not integers. They're true numbers. They're round numbers. They don't have IMDb has basically some decimalization to it, but you don't get 95.1 and 95.2 and 95.3. So it looks a little bit odd. You can imagine what it looks like if you try to do that with ordinal data. Well, with ordinal data, let's see here. I've got this little data set here called bowling alone subset. Actually, I don't want that. So look at this continuous. Oh, maybe that's the one I want to go with. We'll just go with that for now. But the fact is that when you try to do an ordinal variable, you look at something like this variable here, no matter how fast our income goes up, we never seem to get ahead against our family income is high enough to satisfy nearly all our important desires. And these are both measured on a 7-point scale. When you do a scatter plot, it looks like that because there's always somebody who has a 6 on one scale and a 1 on the other. So there are certain techniques you can use called jittering, which kind of shows you where all the data is clustering. But they may find that you need to use a different approach than scatter plots if you're looking at the relationships between ordinal variables. If you did something like a stacked bar chart here, we can see the same two fields shown as scatter plot here, where I've colored it by definitely agree against definitely does not agree. And here we can see that the more one tends to agree, the other tends to agree. So definitely agree tends to be definitely disagree over here. So no matter how fast our income goes up, we never seem to get ahead. Tends to have a lot of the people who definitely agree with our family income is enough to satisfy nearly all our important desires. In other words, they're kind of opposites of one another. One is saying, how much do you agree with the fact that you got enough money? And the other is saying, how much do you agree with the fact that the statement that you don't have enough money? So, if you wanted to show that relationship here, if I were to find those variables here, I'm sure I had that data set. Kendall's comparison. So, Oh, here it is. Yeah, it's here one here. So if I go here and I go to chart builder, I would choose a bar chart here. I'd probably use stacked bar chart. What's this variable here? It says our family income. Let's just check. Our family income is high enough to satisfy all our needs. And no matter how fast our income goes up, it's never enough, really. Let's put one down here. And let's put the other one up there. Stack the colors. Why's that not working? So look. Sometimes you just need to get the. All right, I'm going to hit reset on this. Let's do it again. Okay, sometimes you just need to drop it in. Have a little go with it, drop it in. There we go. So this one here, the colors are a bit confusing. So we actually have a set of our own templates that we can use. And you can download these off our website. So we have a bunch of chart templates. This is one I created called Lollipop. It's a lollipop. Click OK at that point. It produces this way of representing the relationship between these two variables. You can see they're linearly opposite. The more one has a definitely agreed, then they tend to has a higher degree of the definitely disagree category in the other variable. And it's probably one of the more simple ways to represent the relationship, the correlation, if you like, between ordinal variables. Okay, we've talked a lot about correlations here. Let's just finish up talking about the limitations of correlation. So one of the things we get a lot of is you get a lot of people criticizing correlation along the notion of, correlation does not indicate causation. Of course, it doesn't indicate causation. So it doesn't mean that one thing causes the other. It just means that they tend to co-occur. There's a concordance between them, if you like. You do tend to find when you look at examples of this that people use trends rather than scatter plots. It's easier to find trends of cheese consumption here against a number of people who died becoming tangled in their bed sheets, because you tend to get very different things of similar trends, say a double hump or something like that, and you can easily say they correlate with one another. It's harder to find them in a scatter plot. Some people would argue that, yeah, correlation does not indicate causation. In fact, if you're being really really anal about it, you'd say, well, causation doesn't necessarily imply correlation, if you want to come back at them. One thing, it is true though, that when the cases are independent of one another, which they're not with time trends, but when they're independent of one another, correlation does often indicate that there's a relationship, and that's not the same thing. I mean, sunburn and ice cream sales, don't cause one another. Eating ice cream doesn't cause you to be sunburnt. Sunburnt doesn't cause you to eat ice cream, technically speaking, but there is a relationship between the two, and we obviously know what that is. The other thing is as we know, they don't always accurately measure curvilinear relationships. So sometimes people change the data or take square roots of that to try and deal with that, or they use Spearman's rank, which is a kind of simplification of a correlation, to rank them in order to get around the limitations of curvilinear relationships. They are influenced by the range of values in a sample. Here we have a correlation here of education levels against beginning salary. The correlation is 0.633. But if we were to split the range, we look at the split into two groups, and we say, well, look at from $0 to $30,000 as beginning salary, the correlation is 0.6. But after $30,000, if anything, the correlation doesn't really exist anymore. It's close to zero. It's no longer significant at that point. They can be unduly affected by extreme or outlier values. So here we have a correlation here of 0.731. If I add in a value here, a really extreme value here, you can see that affects the correlation here. And the last thing I just wanted to bear in mind is that I did talk about things like significance values. We're talking about significance values here. Let's just do a bivariate correlation here of, let's say, Spearman's against these two factors here. You can see here it's coming out with significance value. The significance value, as I said, it is possible, and we cover this on one of my other webinars where we talk about interpreting significance tests. It is possible to get a statistically significant relationship, which is really, really weak. So in other words, significance isn't telling you that it's a notable or, a useful correlation. It's just simply saying, well, what's the probability that the relationship between these two factors is in fact zero? That's really what it's testing. And if I look at let's look at some bivariate correlations here using the employee data set we had earlier on. I'm just going to look at like previous experience and education level and years and age and stuff like that. Let's just look at those guys here. And the beginning salary. We'll just see if we can find some really weak correlations. So look, there's a correlation there, 0.47. It's non-significant. Here's 0.03, very close to zero. It's non-significant. Here's one here which is significant, but it's really quite weak. I could just add in more here. Look at age and current salary. Let's chuck a few more in here, see if we can find some really weak ones. So, here's one here which is non-significant, minus 0.01. Very, very weak correlation. Here we have current salary against age of employee. That is statistically significant. But look how weak the correlation is. It's minus 0.145. So a word of warning with significance tests is it just, sure, it's statistically significant. It's saying that, the probability that the correlation between current salary and age of employee is zero is relatively small. It's less than 5% because that value is less than 0.05. But it's not, and it's certainly less than 0.01, it's actually less than 1%. But it's not necessarily a very strong or notable correlation. It's one of the classic examples of when something is significant. Just because it's significant doesn't mean it's notable. So, strong correlations tend to be statistically significant, but sometimes very weak correlations are also statistically significant because significance has got nothing to do with the size of the correlation. It's just trying to test the null hypothesis that the correlation is equal to zero in the population. You should be aware that for our customers of Smart Vision, we have free online training materials that are available to SPSS Smart Vision customers. And we also have a range of obviously consulting services that we can work with. People can avail themselves of, whether it be 1 to 2 days or 3 to 5 days. And you can source your software directly from us, including SPSS software. We offer, as I say, formal training and a mix of training and consulting, as well as identification and recruitment of analytical skills in the organization. We generally offer no strings attached advice to anybody that calls us up, whether or not they're a customer for us. If you want analytical advice, then by all means do so. But if you are a customer for us and you're using the SPSS product line, we offer formal technical support services to you, so you don't have to go to IBM to get your technical support. You can give it to us. Does that mean that correlation is only calculated using quantitative variables? Okay, well, it depends what you mean by quantitative variables. All variables are quantitative. Pearson's correlation, it uses scale or continuous variables is the answer to that, which I think we've covered. Whereas Pearson's and Kendall's is more appropriate for nonlinear relationships and for rank order data for such as rating scales, if you want to deal with that. Okay, we will be continuing our webinar series today. We've got another 2 webinars. We're looking at decision trees and we're looking at linear regression. If you're interested in what's beyond correlation, then I'd suggest you register for the linear regression webinar, which we got coming up soon. In the meantime, thanks for logging in, and we look forward to you joining us again in the near future. Thank you very much.